Okay, so here you have a family of 6 periodics that we can animate. This is a family of Poncelet polygons starting here on P1, P2, P3, P4, P5, P6. Out of P1, we're defining these two diagonals, a diagonal connecting P1 to P3 and a diagonal connecting P1 to P4. And then there's a cross diagonal from P2 to P6. And then we define four points, the extremities, the endpoints of the diagonal, point A and D, and then 2 points in the middle, C and B. And I'm going to compute, in the usual sense, the cross ratio of these 4 points, and I'm going to report it here. You guys can see that this number is 0.937959. And now I can actually repeat this computation by moving my base vertex to P2. So I'm going to keep the same kind of three-diagonal construction, but I'm going to make P2 play the role of P1. So let's see what that looks like. So now P2 is playing the role of the previous vertex. I'm shooting these two diagonals to these opposing vertices. Okay, and there's a cross diagonal here, and perhaps it's not so evident, but you can see here points A, C, B, D, just like in the previous picture, A, C, B, D, along this cross diagonal, and I can report this cross ratio here of 2.23. I can repeat this calculation on every vertex. So here's my third vertex. So now P3 is a base, two diagonals leaving from P3 and one cross diagonal. And then I can move on to P4 and so forth and so on. So I can, for each vertex on this family of 6 periodics, I can perform such a construction and then compute the cross ratio that results from this cross diagonal on these 4 collinear points. Now, the first thing you notice with a family of 6 periodics in a Poncelet family of 6 periodics, you notice that out of these 6 cross ratios, only 3 are unique. Okay, so let's go back to P1. That first cross ratio is 0.937. Let's look at the second one when the anchor is P2, 2.23. Let's go to the third one. This one is 0.47. Now, as soon as I go to P4, I'm going to get the same cross ratio that I was getting for P1. You're going to see this. So P4 is giving me 0.9379. You're going to see that this is precisely going back to P1, the one that I was getting on P1. And if I go now to P5, I'm getting 2.23, which is the one I was getting when the anchor was P2. So they're the same. So if the anchor is P2 or P5 or P1 or P4 and finally P3 or P6, they're giving me the same cross ratios. Let's check P3. P3 is giving me 0.47 and P6 is giving me the same number, 0.47. Okay, now the crux of this video is to show what happens as I sum these 6 cross ratios and or I take their product. Okay, specifically, so I'm reporting their sum and their product over here. Specifically, I want to talk about curious phenomenon. The product is equal to 1. The product of these 6 cross ratios, even though there are 3 distinct numbers coming in pairs, their product is 1. Okay, so I'm going to get 0.93 times 2.23 times 0.47. That product of those 3 numbers, which are repeated then on P4, P5, and P6, is going to be equal to 1. And that product is invariant over the family. So I'm going to animate the family here. And you can see here that the product is just stuck at 1. The sum of those cross ratios is not invariant. It's actually a varying number. Now, I can choose a different ordering of the labeling on this cross diagonal here in such a way that I could make the sum be constant but not the product. So let's look at that. Let's go ahead and change. Let's choose another labeling. Let's choose this one, for example. So A, B, C, D maintains a product constant. Let's go to a second labeling. Product is also constant. This is our third labeling that gives us 1. Let's go to the fourth labeling. Fourth labeling also gives us product of 1.0. So you can see here that the labeling A, C, D, B and A, C, B, D both generate constant cross ratio equals to 1, product of cross ratios. Let's go to the fifth labeling. I'm getting constant product of cross ratios, and the final and sixth one also constant product of cross ratios. So there's something interesting going on here that is only becoming apparent to me during the making of this video, that no matter which one of the six orderings that I choose in terms of A, B, C, D along this diagonal, okay, all of them are going to conserve the product of cross ratios as I iterate that construction by making P1, P2, P3, P4, P5, P6 be anchors of this construction. So if I sum them all, I'll get that the sum of those cross ratios is not going to be constant. However, the product will be for all six choices of orderings. And for two of those choices, namely this one, A, C, B, D, and if I just swap the last two vertices, A, C, D, B, for these two choices, my product of cross ratios is going to be conserved and be equal to 1. So finally, one realizes that if you perturb this Cayley configuration here that admits this family just a tad so that the trajectory is no longer closed, this number here is not altered. So let's do that. I'm going to perturb, for example, the axis of the caustic here. So let's go ahead and shrink the minor axis just a tad. You can see now that my trajectory is no longer closing. Okay, in fact, if I continue this trajectory, say along 20 steps, I would not get a closed trajectory anymore, okay? Because I perturbed what had been pre-calculated to produce exactly six periodics, closed six periodics, right? That's almost a redundant thing. If it's a periodic trajectory, it's because it's closed. But now I have an aperiodic configuration. Okay, so I'm still starting from P1, but I do not end up after 6 iterations back on P1. Okay, but what's really curious about this is that the product of the cross ratios, defined exactly as I had defined before, continues to be 1, even though the trajectory is open now. So this seems to be a property of 6 iterations or Poncelet iterations in a pair of nested ellipses. It doesn't matter if they're concentric, if their axes aligned, but as I do this, you're going to see that my product of 1.0 of the 6 so-defined triples of diagonals and their cross ratios, when I multiply those cross ratios, even in this aperiodic, say 6 consecutive vertices of an aperiodic trajectory are still giving me this property. Okay. By the way, if I switch back to an aperiodic, so let's go now to an aperiodic setting here. Now this is an aperiodic trajectory. Okay, I can achieve that product equal to 1 as well. Okay, so I have the same definition. I'm starting from point P1, and I'm defining these first two diagonals with respect to P1, going to P3 and P4, and one cross diagonal. This cross diagonal could be from P2 to P7, from P2 to P8, or P2 to P6, P5. There are many options with n equals 8, much more than there are for n equals 6. But here I'm getting the same phenomenon. The product of those cross ratios is 1. And in this case, I also get that the sum is conserved. So I have a simultaneous result of a conserved sum and a conserved product. Why is that? We have no idea. But what I can show you guys as well is what happens when I perturb the caustic to make this aperiodic become an aperiodic trajectory. So let's do that. I'm going to perturb the caustic a little bit. I'm going to make it a bit smaller, and I'm going to even tilt my ellipse a little bit. Let's tilt it, say, 3 degrees. I've tilted it 3 degrees. You can see that these two axes are no longer aligned, and I'm going to move this guy forward a bit. So I'm going to put 0.1 here. Oops, I should not have done that. Maybe 0.01. Okay, 0.05 maybe, and I'm going to move this guy minus 0.1, let's say, minus 0.01, minus 0.05. Okay, so now I have a clearly non-concentric, non-axis aligned pair. Let's close this down so we have more space. Let's close that and let's close that. Okay, and that. Okay, so now I have a pair of ellipses that are non-concentric, non-axis aligned, and I have a trajectory here. I'm showing the first 8 vertices of it that is not closing after 8 iterations. In fact, if I continue this to say 20 iterations, I would get something that is probably space filling. Let's do 100. Let's do 100. Okay, so this is looking like it's a space filling trajectory. But let's go back to the first eight vertices in this trajectory. Start at P1, go to P2, P3, P4, all the way to P8. And then when I try to close it, I don't close it. You can see that I'm not closing it here. What's happening to that product of cross ratios? It's stuck at 1. In other words, again, we have found a equal 1 product of cross ratios that does not seem to rely or require that the trajectory be closed. So this seems to be an algebral geometric property of iterations, so 8 iterations of this Poncelet map. Okay. Now notice that the sum is no longer invariant. So for the sum to be invariant in this n equals 8 case, I would have to go back to the situation where the trajectory closes. Let's go ahead and do this numerically. So I found here I still have a sort of a tilted non-concentric way, but now the trajectory is closing. So this is a true Poncelet 8 periodic family, and you can see here that now my sum is back to being invariant. So the observations, the preliminary observations here are that both for n equals 6 and n equals 8, you can select 3 diagonals of these trajectories and measure. So once you do that, you're going to get 4 collinear points. You can compute cross ratio for those 4 collinear points under some ordering. There's a specific, or maybe a few out of the 6 possible ones, right? There's a specific set, sometimes 2, sometimes 3 of those orderings. They're going to produce this product of cross ratios equal to 1. Okay? And occasionally you're going to get that the sum of cross ratios is also constant. Now the product equal to 1 remains invariant even when you open the trajectory by tweaking the caustic and breaking away from the periodic configuration. However, the sum does not remain invariant. Okay, so just to redo that, both of them are invariant now. But if I tweak the caustic a little bit, and now my trajectory is going to be open somewhere. Let's see here, I think I tilted it. Well, let's tweak this guy back here. You can see here that my trajectory is no longer closing on P1, right? So I've gone around to start on P1, P2, went all the way around P7, P8. And then after P8, I should be returning to P1, but I'm not. I'm going over here. So if I use these first 8 vertices of this 8 periodic, you can see here that I'm still getting product of cross ratios equal to 1, and that product does not depend on the position of the family. So these are pretty curious phenomena. If you have any insights on why this could be happening, please let us know. See you on the next video. Thank you.